Hello everyone. Today we are going to start a new concept, that is distance of closest approach. Right? So all of you are familiar with this diagram that we know. This is the lid cavity, this is the radioactive source, and what is the radioactive source that was used by Rutherford? That all of you know, it is bismuth, yes or no? And from the radioactive source, what is happening? Alpha particles are emitted. Okay, and what I'm drawing here, this is the what, one gold atom. In case of Rutherford, if we consider the foil is made up of gold, suppose this is a gold atom and this is the gold nucleus. Okay, now what will happen? Suppose the radioactive source is emitting one alpha particle. Okay, so the alpha particle is moving straight in the direction of the gold nucleus, right? And when this alpha particle is moving in the direction of the gold nucleus, what will happen? Its velocity in its path towards the gold nucleus will go on decreasing. Why? This is because whenever the alpha particle will move in this direction, what will happen? Distance of the alpha particle from the positively charged gold nucleus will go on decreasing. As it moves in this direction, the distance from the gold nucleus, positively charged gold nucleus, to the alpha particle will go on decreasing. And since the distance of the alpha particle from the gold nucleus will go on decreasing as the alpha particle moves in this direction, so what will happen? The velocity of the alpha particle will go on decreasing. Why? This is because as the distances goes on decreasing, the repulsive force, right, the repulsive force of the gold nucleus, positively charged gold nucleus, on the alpha particle will go on increasing. Are you getting? In the simple language, what I can say, as the alpha particle is approaching the gold nucleus, what will happen? The velocity of the alpha particle will go on decreasing. This is because he will start experiencing more and more repulsive force by the gold nucleus. So what will happen? The alpha particle is moving in this direction, velocity goes on decreasing, and after reaching a particular point, okay, after reaching a particular point, the velocity of the alpha particle will become 0, right? Here the alpha particle is having maximum velocity. This velocity goes on decreasing, and at here what will happen? The velocity becomes 0, and after reaching this point, the alpha particle will moves back in the same path. Picture is clear? Alpha particle is moving forward, velocity decreasing. Here it becomes 0, and then again reverse back. Right? Now this distance, the distance of this point where the velocity of the alpha particle will become 0, from the center of the nucleus, I am measuring the distance from the center of the nucleus. This distance is called what? Distance of closest approach. That means up to what minimum distance a alpha particle would approach the nucleus, gold nucleus. Is it okay? So distance of closest approach is nothing but the minimum distance, right, up to which a alpha particle could approach the nucleus. Is it okay? Now what we have seen, the velocity of the alpha particle is maximum here at the point of emission, at the point of ejection, and its velocity will become 0 here, right? So the alpha particle is having maximum kinetic energy here at the initial point, and it will have the 0 kinetic energy at this point. Am I right? And we know that energy could neither be created or neither be destroyed. Am I right? It could be transformed from one form to another form. So the kinetic energy the alpha particle is having here, the kinetic energy become minimum at this point. So what will happen to that energy? it will convert it into the mechanical energy. Sorry, it is converted into the potential energy of the alpha particle at this point, right? And we know what is the concept of the potential energy. So whenever an object will have to work against some force, right, then what we can say, then the object must possess an potential energy. Am I right? Whenever an object will have to do work against any kind of force, right, then that object possesses a particular kind of potential energy. For example, if we have to do work against gravity, then we possess gravitational potential energy. Yes or no? Here the alpha particle, whenever it is moving in this direction, right, the alpha particle is moving in this direction, but in this moment at the same time he is experiencing a repulsive force, right? So whenever the alpha particle will have to move further and further, he will have to do more and more amount of work. Are you getting my point? At this point, the repulsive force the alpha particle is experiencing, and at this point the repulsive force the alpha particle is experiencing, if we compare, then what will happen? The alpha particle is approaching maximum more repulsive force here than this point, and that is why whenever the alpha particle will move forward, he will have to do more and more amount of work against the repulsive force of the gold nucleus. Is it okay? And since the alpha particle will have to do work, continuously do work in its forward motion against this repulsive force of the gold nucleus, right, that is why what will happen, its potential energy is goes on increasing in this direction. Is it clear? Here its potential energy is 0, kinetic energy is maximum, and in the forward motion what is happening? Kinetic energy is decreasing and potential energy is increasing, right? And whenever it will reach this point, its kinetic energy becomes 0 and potential energy become maximum. All the kinetic energy will convert it into potential energy here. Now we know that the electric potential at a distance R0, due to the nucleus will be what? 1 by 4 pi epsilon naught ZE by R, because we know this formula of electric potential. So what is that? 1 by 4 pi epsilon naught Q by R. Yes or no? That formula we know. So from that formula what we can say, the electric potential at this point due to the positively charged nucleus will be what? 1 by 4 pi epsilon naught ZE. ZE is what? Charge of the nucleus. That we know, that already we have discussed. Z is the atomic number or number of proton, right? So this is what? Charge of the nucleus, and this comes from this formula. Is it okay? And since the potential, electric potential of the nuclear positively charged gold nucleus at this point is 1 by 4 pi epsilon naught ZE by R naught, this thing is clear because this concept we got in the first chapter. And that is why the potential energy of the alpha particle at this point will be what? That is the electrostatic potential of the gold nucleus at this point, that is 1 by 4 pi epsilon naught ZE by R into charge of the alpha particle, right? That is the charge of the alpha particle. Charge of alpha particle. Is it okay? Is that point clear? So what we will get? We will get 1 by 4 pi epsilon naught twice Z is squared by R naught, right? 1 by 4 pi epsilon naught 2 into ZE, that is twice Z is squared by R naught. This is the what? Potential energy of the alpha particle at this point. Now, according to conservation of energy, here we will consider about the mechanical energy. What will happen? Sum of the kinetic energy and potential energy at this point. Sorry, the sum of the kinetic energy and potential energy of the alpha particle at this point should be equal to sum of the kinetic energy and potential energy of the alpha particle at this point, according to conservation of energy. Now what we consider? We consider that the source of the alpha particle is at a very large distance, infinite distance from the gold nucleus. Why? This is because this size of the nucleus, the gold nucleus, is very negligible, that we are going to discuss a little bit later. It is very small, right? So if the size of the nucleus is very very small, so if we keep this arrangement, this lid cavity not at a very further distance from this, what we can say, from the goal nucleus, then also what will happen, the distance will appears to be at infinite distance for this one, because this size is very very negligible. The size is very very negligible. The size of the nucleus is very very negligible. Am I right? Because of the negligible size, what we can say, the source we consider to be lying at a very large distance, or what we can say at infinite distance for us. Is it okay? Understood? You had the concept of infinity, na? The distance of America for us is what we can say infinite for us. If we have to go to America, right? Not on flight. If we have to go to America on foot, by walking, if we have to go to America. But if we have the opportunity to go through on flight, then it is not an infinite distance. Same concept. The concept of infinite or infinity is different for different perspectives. Yes or no? So the distance of the lid cavity or the source from the goal nucleus is considered to be at infinite distance. Clear? Now what is this? This is what? This is the expression of potential energy, right? This is the expression of potential energy of the alpha particle, of this alpha particle. This is the expression of potential energy of this alpha particle at the initial point, right? This is similar to this formula, yes or no? Similar to this formula. The potential energy of the alpha particle at a distance r0 from the goal nucleus is 1 by 4 pi epsilon naught twice z square by r0, right? At a distance r0 is this one. So the potential energy of the alpha particle at infinite distance from the goal nucleus will be 1 by 4 pi epsilon naught twice z square by alpha infinity, right? Plus this is the kinetic energy. What is the kinetic energy of the alpha particle at the initial point? That is, velocity is v, so half of mv square. And what is the potential energy of the alpha particle at the final point where its velocity will become 0? It is 1 by 4 pi epsilon naught twice z square by r0, right? This r0 is the distance of closest approach, distance of closest approach. And what is the kinetic energy of the alpha particle at this point? At this point, it is again 0 because velocity will be 0. So whenever something is divided by infinity, it will become 0. Half of mv square. In this side it is 0. What is left? 1 by 4 pi epsilon naught twice z square by r0. So what will be r0 from this formula? From this equation, 1 by 4 pi epsilon naught twice z square by half of mv square. Or r0 is equal to 1 by 4 pi epsilon naught twice z square by kinetic energy. So this is the expression for what? Expression of distance of closest approach. Okay. Now we are going to estimate the size of the nucleus. Okay. And this is the basic diagram that we know. This is the source of alpha particle, emitting alpha particle, and here the velocity of the alpha particle becomes 0. This is the distance of closest approach that we know already. Yes or no? Again we are again familiar with this formula, r not equal to 1 by 4 pi epsilon naught twice z square by kinetic energy, where z is the atomic number of the gold, because if we use gold for making the foil, even then the z is the atomic number of the gold. If we use different material for making the foil, then the z will be the atomic number of that particular material. And kinetic energy is what? It is the kinetic energy of the alpha particle. r0 is the distance of closest approach. Okay. Now let us consider two diagram. This is one alpha particle emitted from the source. This is the second alpha particle emitted from the source. And the initial velocity of this alpha particle is 10 meter per second. Let us consider it is much more, it is very much greater than this value. Let us consider. And what is the initial velocity of the alpha particle? It is 100 meter per second. Now, since the initial velocity of the alpha particle or initial velocity means kinetic energy. Since the kinetic energy of the first alpha particle is very much less than the second one, suppose the first alpha particle could move up to this distance, and here its velocity becomes 0 and reverse back. Okay, and the velocity of the second particle or the kinetic energy of the second alpha particle is very much greater than this one. Yes or no? This is 100 meter per second. So what will happen? Since its kinetic energy is more than this one, so it can travel much closer to the nucleus compared to this one. Yes or no? Since the velocity or kinetic energy of the second alpha particle is much more greater than first one, so the second alpha particle could approach or could come closer to the goal nucleus, okay, to much more than the first one. Is it okay? So what will happen here? Kinetic energy is less, R naught is more. Kinetic energy is less, so distance of closest approach is more. Here what will happen? Kinetic energy is more, right? R naught will be less. So if the kinetic energy of the alpha particle will be more, distance of closest approach will be less, and if the kinetic energy of the alpha particle will be less, its distance of closest approach will be more. Alright, am I right? But in both the cases, whatever may be the kinetic energy of the alpha particle, it is not possible for the alpha particle to come inside the nucleus. Yes or no? Because the nucleus is wholly positively charged. Right? So this is the nucleus. Right? The alpha particle could not go inside. It is not possible. Could not go inside the nucleus. Right? Because both are positively charged. If it will go inside, that means it will become attraction. Yes or no? And we know that is against nature, that a positively charged particle could not attract a positively charged particle. Right? So the only possibility is that if you give maximum kinetic energy to an alpha particle, it will go to a very what we can say, very closer distance. If we give kinetic energy, if the kinetic energy of the alpha particle will be maximum, then it can go to very closer distance to this goal nucleus, but it could not come inside the nucleus. Understood? Why it could not come inside the nucleus? Why the alpha particle could not come inside the nucleus? Because if the alpha particle will go inside the nucleus, then it will not become repulsion, it will become attraction. Yes or no? It appears to be attraction, which is not possible between two same kind of particles. So if you give maximum kinetic energy, so it can go to the minimum distance. It can approach the goal nucleus to the minimum distance. Is it okay? That point is clear. Now what will happen? Let us come to the formula again. R naught is equal to 1 by 4 pi epsilon naught Z E square twice Z E square by kinetic energy. Right? Now we know the maximum kinetic energy of alpha particle emitted by a radioactive source is always 7.7 mega electron volt. Right? And we know the value of 1 by 4 pi epsilon naught is 9 into 10 to the power 9. Right? Let me write down the value first of all. 1 by 4 pi epsilon naught is equal to 9 into 10 to the power 9 Newton meter square per coulomb square. Right? Z is 79 for gold. Right? For different material it will be different. Is equal to 1.6 into 10 to the power minus 19 coulomb. And what we say, the kinetic energy maximum kinetic energy of an alpha particle could be what? Maximum alpha particle kinetic energy of an alpha particle could be 7.7 mega electron volt. Now if you put all this value here, 9 into 10 to the power 9 into 2 into 79 into it is E square. Let us consider E square, keep it like this way, and this 7.7 into 10 to the power 6 electron volt. Okay, because mega electron volt means 6.6 in 7.7 into 10 to the power 6 electron volt. Is it okay? So what we got, you can check, you do this keep it as homework, you try it, do the calculation. that it comes in the range of what? It comes in the range of 10 to the power minus 15 meter. Okay, do the calculation. It comes in the range of 10 to the power minus 15 meter. Okay, that means that is the minimum distance. That is the minimum distance to which a alpha particle could approach the nucleus, right? Because 7.7 mega electron volt is the maximum kinetic energy that I am using, right? The kinetic energy of the alpha particle could not go beyond that 7.7 mega electron volt. Is it okay? So this is the minimum distance to which a alpha particle could reach or approach the nucleus, goal nucleus. So obviously the size of the nucleus could not be greater in this value, could not be greater in this range. Am I right? It will have to be either smaller or equal to, maximum equal to or smaller to this value. Is it okay? And that is why what we can say, the radius, the size radius of a, what we can say, of a nucleus, that's what we can say, the radius of a nucleus is always in the range of 10 to the power minus 15 meter, right? And this range is having a particular name. It is called 1 Fermi. 10 to the power minus 15 meter is equal to 1 Fermi. Okay, this is a new unit of length, right? 1 Fermi is approx size of the nucleus. Is it okay? Understood? Okay, let us do a numerical. What is the numerical? 0.640. So let us do one numerical. Let us solve one numerical. And a alpha particle of kinetic energy 5 mega electron volt are projected towards uranium nucleus having atomic number Z is equal to 92. Find the order of the distance of closest approach. Here gold foil is not used. Here what is used? In place of gold foil, uranium, right? Uranium foil is used. Let us consider this is given like that way. Now this is the atomic number of the uranium, that is 92 given. You have to find the distance of closest approach. Actually you have to find the range of distance of closest approach. So let us solve it. We know that R naught is equal to 1 by 4 pi epsilon naught twice Z square by, what is the formula? Kinetic energy, right? And 1 by 4 pi epsilon naught is how much? This 9 into 10 to the power 9 Newton meter square per coulomb square. Z is given 92. E is equal to 1.6 into 10 to the power minus 19 coulomb, and kinetic energy is given. Kinetic energy is how much? It is 5 mega electron volt, or 5 into 10 to the power 6 electron volt. So R will be 9 into 10 to the power 9, right? Newton meter square per coulomb square into 2 into 92 into here. Let us write for the time being, it is E into E, 1E into 1E, and here it is kinetic energy is how much? 5 into 10 to the power 6 electron volt, that is 9 into 10 to the power 9 into 2 into 92 into 1E into 1E. It is 5 into 10 to the power 6 into 1 electron into 1 volt, that you know, right? This one electron and 1 electron, 1E will get cancelled. What is left? 1E divided by 1 volt. So it is 9 into 10 to the power 9 into 2 into 92. 1E means 1.6 into 10 to the power minus 19, right? And here it is 5 into 10 to the power 6 into 1 volt, right? And Here the unit of 9 into 10 to the power 9 is how much? Newton meter square per coulomb square, and 1.6 into 10 to the power 19 is it is coulomb divided by 1 volt, right? And here it is 1 volt, because I will write in the next part. Okay, so it is 9 into 10 to the power 9 into 2 into 92 into 1.6 into 10 to the power minus 19, 5 into 10 to the power 6 Newton meter square, coulomb to the power minus 1, coulomb to the power plus 1 is coulomb to the power minus 1, divided by 1 volt. 1 volt means what? 1 joule by 1 coulomb, because V is equal to W by Q. Again W is equal to force into displacement Newton into meter. So what we can write, this value for this calculation, whatever you will get the value 640 into 10 to the power minus 16. Now what will happen to the unit? Newton meter square per coulomb. This coulomb will go upside. Coulomb joule means 1 Newton into 1 meter. 1 Newton will get cancelled. This one will get cancelled. The meter square by meter will give you only meter. 10 to the power minus 16 meter. That is 0.640 into 10 to the power minus the same thing. 640 is equal to 0.640 into not 10 to the power minus 3, 10 to the power 3, right, into 10 to the power minus 16 meter. It will give you 0.640 into 10 to the power plus 3 minus 16 is equal to 10 to the power minus 13 meter. That is again equal to 0.640 into 10 to the power minus 13 meter. So you have to multiply it by 10 to the power 2 if you have to convert into centimeter. So the final result, what I will get here, 0.640 into 10 to the power minus 13 plus 2 is equal to minus 11 centimeter. So this is the correct answer.